Hi, everyone, and welcome to the Wastewater Process Emissions webcast series. We are happy to partner with various organizations to present 4 webcasts in this series. Today is the third in the series, titled Nitrous Oxide Emissions from Wastewater Treatment. My name is Michelle Suazo, and I wanted to run through a few housekeeping items before handing it off to our research principal, Dr. Harry Zhang. You are allowed to submit questions through the question box at any time. We will hold all questions and do a question and answer session at the end of the webcast. Slides and a recording of the webcast will be available on our website, and you will also receive a follow-up email that'll have a link to the recording and to the slides once we're done with the webcast. You can also download the slides now under Event Resources on the bottom left of your screen. And you can also access some resources from our website. If you decide to get to our website, you can pull some things from there as well. A certificate of completion will be automatically generated. If you have any questions or problems with that, please reach out to me. You can see my email there. And then please also do stay on till the end and fill out the survey. That just kind of gives us some feedback as to how we're doing with our webcasts. So with that, I'm going to go ahead and send it over to Harry.
Hi, thank you, Michelle. So I'm Harry Zhang from the Water Research Foundation. So I want to use 2 to 3 minutes, give you a little bit overview on the Research Foundation, climate mitigation and the greenhouse gas emission research. So since our first webcast in July, Research Foundation have received a question. So what is your general portfolio on the greenhouse gas emission and also climate mitigation? So I want to use this slide just to convey. So the Research Foundation divided, I think, our research into like maybe 3 subtopic. So the first category is like a greenhouse gas inventory and also the data library. So we have 2 projects ongoing at the moment. The first one is on the industry-wide guidance for the water utility life cycle greenhouse gas emission inventory. Second one we just got started is on the greenhouse emission library for the unit process, and then they cover both the drinking water, wastewater, stormwater utility, and also even all the way to the decentralized systems. These 2 projects are one water project. So the second subcategory is on the greenhouse gas field monitoring and also method comparison. So as you can see here, we can drill into like a fuel methane monitoring and also nitrous oxide monitoring, which is part of this talk here. And then the third category, and also including one upcoming RFP talking about a method comparison. So this is for both methane and nitrous oxide. So and then the third category is on the broader, I think, a climate mitigation thing. This is involved use a multi-criteria decision making at utility. For example, how to balance the trade-off among treatment process and then the greenhouse gas carbon management and also energy efficiency. So if you want to looking for some current research work from Research Foundation, so this slide will help you to navigate through our website. I think we have a climate change topic hub, and then we have a total of 80 climate research studies across wastewater, stormwater, drinking water, and reuse water. So they cover category like a climate adaptation, mitigation, greenhouse gas emission, and also a risk assessment. With that, let me pass to David.
Thank you, Harry, for that welcome, everyone. My name is David Ponder. I'm the Director of Climate Action at the U.S. Water Alliance. I'm going to introduce us to the webinar series overall, and I want to start first by acknowledging and thanking the contributors who have made this presentation possible. So this project is a collaboration between the U.S. Water Alliance and the Canadian Water Network, hosted by the Water Research Foundation and with the support of the International Water Association, Water Water Environment Federation and the Danish Water Technology Alliance. We want to say thank you for your support. Next, I want to kind of turn to a little bit of the big picture in terms of why this is an important topic. The water sector has issued a call to action to achieve net zero greenhouse gas emissions by 2050. That is in line with the Paris climate agreements. And if some of you all saw the news last week, unfortunately, we collectively are not on track to meet those goals, and that we need to accelerate our efforts to reduce our greenhouse gas emissions to avoid the worst consequences of climate change. And some of you may be wondering, well, why the water sector? Well, the answer is, well, we're not as big as the energy sector or the transportation sector. We are a non-trivial contributor to greenhouse gas emissions globally. Our current best estimates suggest that we're about 1.6% of global greenhouse gas emissions. And that's on par with other high-profile sectors like global shipping and aviation. And process emissions are an important source of those emissions from water and wastewater utilities. And that's why we're holding this series. So we as a sector can come together to have a conversation about the types and sources of emissions that come from our facilities, what the mechanisms and processes are that give rise to those emissions, what the techniques for measuring and monitoring those emissions are, and what we can do to reduce those emissions. So as Harry and Michelle indicated, this is the third of a 4-part series. The recordings for the other series are available online. Today, we're going to focus in on nitrous oxide emissions, and we're going to conclude the series in December with a conversation about mitigation strategies. It's my great pleasure to talk a little bit about who's going to be speaking to you today. You have two of the best and the brightest folks in the sector who've been thinking about these issues for quite a while. First, we have Shen Kavanaugh from Brown and Caldwell, who's going to give you all an overview of nitrous oxide emissions from wastewater treatment, followed by Emma Shen from Jacobs, who's going to comment more about sort of the techniques to measure those emissions. And then we're going to hear from Aaron Jacobson from King County about their experiencing measuring greenhouse gas emissions. So without further ado, I'm going to pass the mic to Shannon.
Thanks, David. So today I'm going to be giving a pretty brief overview of nitrous oxide emissions from wastewater treatment before Emma gets into some of the monitoring strategies and Aaron goes into kind of a case study of direct measurement. To provide some broader context of why we're talking about what we're talking about today, we have all seen the impacts of climate change more and more every year, specifically Hurricane Helene this year, which has just had such devastation. We're really starting to feel the impacts of climate change. When we see these events happening, a lot of times you're having to work on adaptation to the problem. In our wastewater utilities and as consultants doing design, we are thinking about how do we design our treatment plants to withstand these kinds of new challenges, how will our infrastructure survive. However, the topic we're focusing on today is kind of looking ahead of that and how can we build in mitigation to what we're doing as an industry. Wastewater treatment plants are highly engineered systems that provide a really unique opportunity to mitigate greenhouse gases. And as we think about our utilities, which were initially formed to protect environmental and human health through water treatment, we should really think about how climate change fits into that conversation and how climate change also relates to environmental and human health. So background on nitrous oxide. Nitrous oxide is one of the 3 major greenhouse gases that we think of at a wastewater treatment facility. This figure on the right is demonstrating the different magnitude of different greenhouse gas molecules. So nitrous oxide, N2O, one molecule of N2O over a 100-year time span up in the atmosphere has a 273 times stronger warming effect than one molecule of CO2. And methane is still 10 times smaller than nitrous oxide as well. So even if your emissions are relatively low from a mass perspective, nitrous oxide is extremely important to focus on because of its huge global warming potential. I'll note that N2O is different than NOx, which you may have heard of as a harmful air pollutant, but NOx is not a greenhouse gas. It has other harmful effects. N2O is the greenhouse gas, nitrogen oxide. So 40% of emissions are anthropogenic. This chart on the bottom is from the EPA, and while agricultural soil management is the largest source of anthropogenic nitrous oxide emissions in the US, wastewater treatment is about tied for second place. And as a proportion of all emissions, as David mentioned, this is a non-trivial source of emissions in our society. So how is N2O formed? Primarily, it's formed at wastewater treatment plants in aeration basins as a byproduct of nitrification and denitrification processes. So in this figure on the right, we're kind of showing all the nitrogen transformations that can happen in your secondary biological treatment process. First, I'll touch on in the upper right, you have the oxidation of ammonia to nitrite, which is the first half of the nitrification pathway that you'll see in a nitrogen removal process. Hydroxylamine, or NH2OH, is one of the intermediates of this nitrification process. And there's then a chemical reaction with oxygen to create N2O as part of the ammonia oxidation pathway. So while it's actually a chemical reaction forming the N2O, the hydroxylamine is formed through a biological process. So we call it like a pseudo-biological process. And that is where you're seeing emissions from the nitrification step. The next two pathways are denitrification pathways. So on the bottom, we have the heterotrophic denitrification pathway where you have nitrate reduced to nitrite. And then on the way to being fully reduced to nitrogen gas, which we think of as the full nitrification pathway, one of the intermediates is N2O. In the lower left, we're kind of seeing the full denitrification pathway with the different genes that are responsible for these different transformations. However, for whatever reason, and we'll get to the triggers a little later on, if you cannot fully reduce to nitrogen gas, that dinitrogen gas, you will emit N2O through your process. So emissions are extremely variable. This could be diurnal variability. In the kind of upper middle figure, we're showing just several days at a treatment plant, which Erin is going to talk about that plant in particular. We see in the rainbow colors the different diurnal variability of all different parameters at your treatment plant, which is what you see at all treatment plants. It changes throughout the day. Your flows and loads have swings up and down, peaks and troughs. However, we see that nitrous oxide in the dotted blue line on that chart has much more significant peaks and troughs, peaking quite high and going down to essentially zero, even while you still have some nitrogen loading down in those zero emission periods. So we see significant diurnal variation. We see seasonal variation based on temperature, flows and loads, operational conditions at your treatment plant. And then in general, emissions are extremely variable depending on your specific process. So this is amongst different types of configurations, whether you're removing nitrogen or not in your process, but even amongst processes of the same configuration, for example, in the lower right-hand figure, all of these processes, but for example, you look at the MLE, box and whiskers, there's 30 MLE plants in this study, and the range of different emissions observed is just drastic. So the three figures that I'm providing here are from some really great papers that I recommend folks check out if they're interested in digging into this a little bit more. These are pretty comprehensive literature reviews and meta-analyses that are kind of diving into the state of research at this point of different full-scale monitoring that has taken place and kind of comparing and contrasting. So what is leading to the significant variability that we're seeing amongst these different configuration types, operational conditions, day-to-day, et cetera? So there have been a lot of studies that have researched what is causing elevated emissions at our treatment plant or another treatment plant. It is difficult to make generalizations, as you saw on the slide before. It varies so much plant to plant and configuration to configuration, but some broad generalizations that have been kind of formed over many studies are listed here. And it doesn't mean that it will necessarily cause problems at your plant, but it could. So for example, rapid drops in DO concentration or not well-controlled DO, nitrite accumulation in your aeration basin, low COD-N ratio during denitrification. So that's not being able to meet the carbon demand of your denitrification process. The presence of biological nutrient nitrogen removal. So this is a little bit misleading because I've heard questions from utilities saying, well, we are a conventional activated sludge process. We don't have a nitrogen permit. Can we say that our nitrous oxide emissions are zero? Can we say that in our official or unofficial greenhouse gas inventory? And it's a little dangerous to make that assumption because, as I'm sure some of you have observed at your plants, even if you're not designed for nitrogen removal, in the summer, your SRT can creep up, the temperatures will be warmer, you might not be monitoring your effluent nitrogen levels because you're not permitted, and your plant will experience some transient nitrification in these summer months or throughout the year. And actually these transient periods can lead to extremely high emissions as well, sometimes even more than a very well-controlled DNR process that is operated very steadily with very high process control. And finally, rapidly changing process conditions, shocks to the systems or process upsets have been associated with significant peaks in N2O emissions. The current mitigation strategies to reduce nitrous oxide at a treatment plant focus on increased process control. I won't dive into that too much because the next webcast on December 12th will really get into that further. But as you can see from these different emission triggers, and perhaps the process engineers in the audience will know that a lot of these triggers are caused by or will cause problems in your biological process. So next, there are other potential emission sources of N2O at your treatment plant, and it really depends on the process you're operating. If one of these that I list here will be a more significant contributor than your aeration basins. So it really depends plant to plant. As we all know, no two wastewater treatment plants are the same, and it really requires participation from engineers and operators to kind of figure out where the N2O is at your plant in particular. Other emission sources include side stream treatment, which can often actually be larger emitters than mainstream treatment, depending on the plant. Post-aerobic digestion, disinfection, and that is actually a potential chemical reaction between hydroxylamine and hypochlorite. Solid storage, and then sludge incineration, finally, can actually be a quite significant source of N2O. So to estimate nitrous oxide emissions at your treatment plant, there are kind of different tiers for estimating and putting these numbers into your greenhouse gas inventory. I'm going to list these from kind of easiest and worst data quality to best but most difficult. So first, we have a method from the IPCC, which is using a nitrogen loading assumption based on protein intake and population numbers. This method is actually developed more so for countries or regions that do not have data about nitrogen loading to their wastewater treatment plants, just basic flows and loads data. And I would not recommend using this method for a wastewater utility in the United States. Even if it's a small facility, you should be able to do some pretty basic sampling to avoid using this emission factor. The next, and I'd say most popular method to estimate your nitrous oxide emissions is to use the default emission factor recommended by the IPCC, which is 1.6% of your influent TKN emitted as N2O. I think it's N2ON actually. So, but this is a pretty general emission factor that is based in some studies, but it's important to note that, as I mentioned before, your treatment plant is, I'd say, almost guaranteed to not have this exact 1.6% number. This order of magnitude is generally what we expect from a nitrogen removal aeration basin. However, if you are trying to build your greenhouse gas inventory, these, a 50% difference in this number can actually have a ginormous impact on your portfolio as a whole, and then you deciding what to do about different emission sources. I would say the next best approach is using an emission factor from literature. This is the figure that I showed before from this literature review that was recently released, and I do recommend folks kind of look into some of this data if they're really curious about what might emissions look like at my plant with my process. However, I recommend to take this data with a grain of salt and understand that no two treatment plants are the same. Finally, I'd say the gold standard is direct measurement, which Emma is going to discuss in her presentation. So we still have questions about nitrous oxide emissions from wastewater treatment. These are kind of FAQ that I get, and the answer is always, well, the science is developing, research is currently happening, but we just don't yet know. So this includes, what are the dominant pathways and mechanisms for N2O production? We know which ones exist based on the figure I showed before, but we still don't yet really understand kinetically why one may dominate the other in your process. Are there BNR technologies that are necessarily high or low emitters? I'd say there are hypotheses in the industry right now that certain mainstream processes may be good low N2O technologies, but the data does not yet exist to defend that claim or give a manufacturer guarantee. And it's highly dependent on operations as well. And then for necessarily high emitters, we believe that side stream could be a necessarily high emitter, but really we need more and more research and really understand the operation of these systems to jump to any conclusions. Can we accurately model or predict N2O emissions? And then what is needed for N2O mitigation, and how effective are these efforts? So my final slide, I will just provide a few drivers for N2O monitoring and mitigation. For the folks in the audience who are curious about N2O, these are kind of some nuggets that may be helpful as you think through what you want to do as a utility about nitrous oxide. So the first one is decarbonization in every sector is essential to combat climate change. This is the note of it's the right thing to do for our industry. City climate action plans and net zero goals include wastewater utilities, whether the wastewater utility was included in setting these goals or not. We see some utilities that have a net zero goal from their city, and now their city is asking, why aren't we net zero? And the utility has to respond because N2O is a big question mark for us. Process emissions can be the biggest contributor to WRF greenhouse gases, especially as energy efficiency improves on site and the grid decarbonizes, meaning that with your slice of the pie of CO2, methane, N2O, electricity, chemicals, as the other slices get smaller in terms of carbon footprint, the process emissions become the most important to focus on. N2O emissions are uncertain until they are measured, which I touched on before. And then finally, there can be some co-benefits of N2O mitigation. I believe the mitigation webinar will speak to this more, but N2O mitigation can go hand in hand with process control, energy efficiency, capacity improvement, and increased performance. And secondary treatment optimization projects can really focus on all 5 of these parameters, and it can be a win-win in terms of performance and mitigating emissions. So with that, I will thank you guys, and I will pass it to Emma next.
Thank you. Okay, so now I'm going to talk about direct measurement of nitrous oxide emissions. So when we are quantifying nitrous oxide, there are different methods out there. You can measure it at site level, or you can also measure it from bottom up at source or process unit level. Which one is best suited for your purpose really depends on what you're trying to achieve. Are you trying to baseline your site-wide emission, or are you trying to identify and maybe mitigate the different sources? But overall, the plant level measurement provides less granularity. Some methods can be continuous, which would be good to support your baseline quantification and captures your operational and seasonal variations, but others are more intermittent, and it's still good if you're trying to have a snapshot to help you prioritize across different sites or different sources. And most importantly, when we report greenhouse gas emissions, we need the mass emission rate, but the methods typically measures a concentration. So we'd need some computation or modeling to convert your measured concentration to a mass flow rate. So just kind of give you a big overview before we dive into the different methods. So this slide is a really high-level overview of the current quantification approaches that have been applied at water resource recovery facilities. So there's kind of a wide range of technologies that are out there. You don't have to read the slide. I will give you examples for each of them in the next couple of slides. But as I mentioned, you have site-wide method, you have process unit method. Some method can do both depending on how you design it. But overall, the message is process unit measurement is fundamental for mitigation, and both liquid and gas method are beneficial in this case. So now let's talk about each one of them. I'll give you a bit of example as well. So the first one is trace gas dispersion method or tracer correction. So this is a plant-wide measurement. Typically, you have a ground-based remote sensing method. So you have a vehicle mounted with gas analyzers, and then you have a controlled release of tracer gas from your plant, and then you can measure the concentration downwind. So this method is probably the most commonly used for wastewater treatment facilities, at least based on what we can find in literature. It does require a lot of special techniques. So far, it's largely limited to the academic practitioners. It is recognized as the more accurate method, especially for intermittent measurements. There are some limitations. You need some distance from the site to ensure the nitrous oxide and your tracer gas plumes are well mixed. And also, if you do have some masking or interference sources from upwind direction, then there's potential for more uncertainties or errors. The next plant-wide method is called inverse dispersion modeling method. So instead of using tracer gas, in this case, you strategically deploy concentration measurements across your site. And also you will need some weather station to collect the weather data and use the information in inverse dispersion model to quantify the site-wide emission rates. Similar to tracer gas method, this one is also largely relies on academic skill set, at least for our sector. Because it relies on, you can deploy sensors, and on a long-term basis, it does give you the opportunity to do continuous measurement. Compared with the tracer gas method, it has slightly lower accuracy, because it does rely on the wind conditions, and also there are uncertainties associated with the dispersion modeling itself. A more emergent method is using drones. So instead of having vehicles on the ground, you can also mount the gas sensors and weather sensors on the drones and then fly over the site in some well-designed route and software drone flux, so you can estimate the mass emission rate. So the strength of the drone method compared to the ground-based method is it gives you sometimes better accessibility to some hard-to-reach areas since you're doing it from the high elevation. Some of the limitations, it is only a snapshot, like the intermittent measurement, because you have limited drone battery life. You can probably fly, a couple of hours. And sometimes there are site restrictions. So if your plant happens to be near the airports, or if you have atmospheric explosive nearby, then you may not be able to easily fly a drone over. This does not apply to every single plant, but in some cases, you do have fully enclosed wastewater treatment plants. So this example is the Väkimäki wastewater treatment plant in Finland. It's underground, and they have all of the process emissions captured and then vented through a single stack. So it provides a pretty good setup for you to do continuous gas phase measurement. In this case, you need gas analyzers. There are different analyzers available out there, but you would also need gas flow measurements in order to calculate your mass emission rate. So if you happen to have enclosed process areas with this kind of setup, this is really good for long-term measurements, capture all of the emissions from covered processes, but then it does not really measure the spatial variability, so you may not provide enough evidence to support mitigation. And I will probably emphasize this for every single slide from here, is accurate flow measurement is really important for any kind of nitrous oxide emission measurement. In the case of this Väkimäki plant, instead of using gas flow meter, they calculate the gas flow based on the pressure and fan operation. Now, because in sometimes it might not be feasible or practical to install gas flow meters. It could be confined space entry, some other restrictions. But for this plant, in addition to the gas phase measurement, they also use liquid phase monitoring for research purpose and for developing mitigation strategies. So those are plant-wide or site-wide measurement methods. So the next two slides, we're talking about process unit level measurement. So the first one is flux chamber or floating hoods method. So you put a hood on top of your, for example, the aeration tanks. You collect the off gas from the hood, and then you measure the gas concentration using an analyzer. So this one can be used for both continuous or intermittent measurement. For measuring nitrous oxide emissions at water resource recovery facilities, there is actually a US EPA endorsed standard method that was developed by Professor Kartik Chandran from Columbia University. So as you can see, the equipment here is a little bit more complex compared to which I will show next when you measure it in the liquid phase. So you have the hood, you need the analyzers, and also the gas samples typically require some conditioning before you can send it through the gas analyzers. When you're doing process unit level measurements, especially if you can move the hood around or having multiple hoods, it gives you the opportunity to investigate the dynamics and the spatial variability of the greenhouse gas emissions. And depending on the type of analyzers, you can measure multiple gases, including methane and oxygen and some of the other gases. And the challenge of using unit level measurement is that you only have a small gas hood, so you only measure the gas below the surface of the hood. So how do you extrapolate that to your entire tank or the entire plant? There's always some uncertainties associated with that. And again, accurate flow measurement is essential, and I will show you some examples later. So all of the previous method I just presented, they can be used for both nitrous oxide and methane measurement. This one is specific to nitrous oxide only. So there is a sensor. Currently, this is the only commercial sensor that can measure the dissolved nitrous oxide in your liquid phase, like in your wastewater. And then you convert this to the gas phase emission based on Henry's law and your aeration airflow rate. So as you can see, the equipment is a lot simpler. You don't need a hood or sample conditioning. If you have multiple sensors, similarly, you can try to deploy it strategically and investigate the dynamics and the spatial variability of the greenhouse gas emissions. The similar challenge about how do you extrapolate from a single or 2 points to your entire larger process areas. Another consideration is this sensor is sensitive to the wastewater temperature because it does rely on the Henry's law to convert to the gas phase emissions. So calibration is required if your wastewater temperature changes from more than ±3 degrees Celsius. So for example, where I am at in Southern Ontario, in spring season, we do see like snow melt. So there's pretty significant temperature drop in that period. So you do need to keep an eye on your sensor and do the calibration as needed. I think the strength of the sensor is it allows you to do some long-term continuous measurement. And when we do measure, some of the examples here is showing that they are very dynamic, like Shannon mentioned. So measurement across seasons and across different zones will be critical. And I guess I kind of already alluded to this, is when you're measuring at process unit level, how many sensors are enough and where do you measure? I don't think we have reached a consensus yet, but generally speaking, if you have like a complete mixed system, maybe a single probe or two, if you have dedicated aerobic or anoxic zones, then that's probably enough. So that's the example to the left. But when you have those long plug flow aeration tanks, like I'm showing an example to the right, you can see the emissions are different within different zones. And for each zone, they are different over time. So for plug flow reactors, multiple zone monitoring will be critical if you want to try to accurately the emissions. There are some validation works trying to compare the accuracies between different methods. So this slide is showing some examples trying to validate between the gas phase measurement and the liquid phase measurement. The example to the left is a long-term validation at a full-scale wastewater treatment plant when they have the enclosed plant, so they can measure based on the liquid measurement calculation and the gas phase measurement from the enclosed plant. And the example to the right is a more recent work out of Germany. They are comparing the liquid sensor versus the gas hood, so still show pretty good correlation between the two methods. And then more recently, there are more work, mostly in Europe, trying to compare the process unit level measurement versus the site level measurements. So this is recent work from the wastewater sector. They are trying to compare the hood method from multiple lengths versus a site level drone flux method. So as you can see here, the message continues is that airflow data is key. Those different blue shades bars are depending on how you get your airflow data, the estimated emission could be quite different. And sometimes you may need to estimate your air based on the valve positions or blower details. There is another really good study with publication pending. It's the Danish AWARE study. This will include long-term comparison of multiple methods from both process level and site level. And really just to bring this up again, most of the time, the concentration measurement can be pretty accurate as long as you're measuring within the detection range of the sensor you choose. This is an example where we have an airflow meter that's 3 times wrong. So as you can see, the uncertainty here is way higher than the analyzer inaccuracies. So some key takeaway messages in direct nitrous oxide measurement. So far, we still don't have like an industry standard or guidance on how do you measure it at a wastewater treatment plant, but the global work is ongoing. Many measurement technologies are available and comparative work is ongoing. All methods require some assumptions to calculate and compare the emissions, but good quality process data is critical. Efforts are needed towards unifying the best practices for a robust and reliable measurement of N2O emissions in practice. But please do not let that deter you. We know enough to start today, and really mitigation starts with measurement. And with that, I just want to share with you this really exciting global collaboration for N2O measurement. This is the upcoming WRF project. We are about to kick it off very soon. Jacobs, along with Princeton University, will be the co-PIs, and we have 25 global utilities collaborating on this project. And I will leave with you some additional resources. It has a link here. You can download those reports and open source books. It has more information on a lot of the comparative studies and the literature references. And then I'm going to pass this over to Aaron.
I'm Aaron Jacobson. I'm a wastewater engineer at King County. King County provides wastewater treatment services for the greater Seattle metropolitan area. I'm going to talk about our N2O emission measurements at 2 of our regional treatment plants, our Brightwater treatment plant and South treatment plant. The real reason we started measuring nitrous oxide emissions was because of a capital project to improve the performance of our secondary treatment system at our Brightwater treatment plant. During the process of selecting conversion to simultaneous nitrification, denitrification, or we identified that there's a potential to have high nitrous oxide emissions with low DO conditions. So even though the project was going to save energy and supplemental alkalinity, there was a potential we would have higher emissions, and we wanted to know whether or not that was happening. So we wanted to baseline with our previous or our current configuration, and then measure emissions after we make that conversion. Since we hadn't measured nitrous oxide emissions before, we wanted to compare a couple different techniques with an aqueous and gaseous measurement approach. And then we've been doing a carbon footprint at King County for about 20 years. And we had been using the 2006 IPCC methodology. And we thought, well, if we get data that we can feel confident in, we can improve upon that. Similar situation in our South treatment plant, we were having a process change of our secondary treatment system, at least seasonally, to go from our conventional activated sludge to a Bloodsack Edinger nitrifying configuration to remove nitrogen to comply with new permit conditions. And similar similar story around the carbon footprint improvement potential. Our Brightwater treatment plant is a MBR plant. It processes about 18 mgd of wastewater on average. It's fully nitrifying for the membranes, and I describe it as a pseudo MLE configuration. It has a very small anoxic zone that is about 10% of the total volume of the aeration basin. It has a pretty low mixed liquor recycle, and the RAS returns up to the first aerobic zone. So it's not, it looks like MLE on a schematic on paper, but it doesn't necessarily function that way. Both the membrane basins and the aeration basins are totally covered. There's an odor control system that keeps a slight negative pressure on the headspace of those basins for odor control, but that also theoretically pulls all of the nitrous oxide emissions from those two basins through the odor control system, which is convenient for gaseous measurement. So I've shown there the different sample points where we measured nitrous oxide emissions at the odor control. And then also we installed aqueous probes in one of the 3 aeration basins. I'll talk more about that. The gaseous analyzer we used was a Teledyne gas filter correlation infrared analyzer. It was supposed to be an environmentally controlled enclosure. We made a pseudo environmentally controlled enclosure with a sample train to pull a sample, remove moisture and particulate, and condition it for the analyzer. The whole cart is mobile, so we can measure different locations and then take it to different plants. As I mentioned, theoretically, if we're measuring the concentration, the total concentration of nitrous oxide, and can measure the airflow through the odor control system, we can get a good measurement of nitrous oxide mass flow that's being emitted there. So it's a good measurement, but not super useful because it's not in a permanent enclosure, and it is maybe a little more finicky and requires more care than the aqueous probes, which I'll talk about. As Emma mentioned, the only analyzer that's available as an aqueous probe is the Unisense Clark type probe, electrochemical probe. We installed 2 probes and the controller. The first probe we located just downstream of the anoxic zone where the flow falls over Weir into the aerated zone. We couldn't access the anoxic zone directly from above, so that was the closest point where we thought we could sample to get a representative concentration of nitrous oxide in the mixed liquor from the anoxic zone. Second probe we located in our second aeration zone, about a third of the way down the aeration basin. The probes themselves and the controller are fairly similar to other wastewater probes. I mean, it looks pretty similar to a GO or pH probe with a controller, like something like from Hawk or YSI. So there's a familiarity there. You can integrate it into your SCADA system and have it do internal calculations to spit out emission estimates if you feed it airflows. We did all that post-processing to make the installation real simple. But we do definitely see it as easier for long-term measurement. Doesn't take a ton of calibration, and it could be integrated into controls in the long term. So our first campaign of measurements of Brightwater, which Shannon helped with, we did the comparison of the aqueous and gaseous analyzers, and they both had very good tracking of diurnal variations and picked up on changes in influent loading. So they were quite responsive, and as you can see, like their tracking matched pretty well. The only difference is the aqueous analyzer, or the estimate from the aqueous analyzer, was high by some. And since our gaseous measurement was our gold standard, we decided to apply a factor of about 2/3 to the aqueous data to make it better match the gaseous emission estimates. Maybe a reason for the aqueous analyzer to read high here, we theorized, was that Brightwater is somewhat unique in that it has very deep basins. They're 25 feet deep, and then pretty high mixed liquor suspended solids concentration because of the NBR. So we took the approach of long-term measurement with the aqueous analyzer, and we've been measuring for the better part of 4 years. We definitely have seen variation through the years and within a year, so seasonally. Overall, our average emission was about 0.42% of the TKN influent to the plant. Just leave it as nitrous oxide. That's our best estimate. We haven't actually gotten to test operation with SND. The capital project that we baseline for is coming to completion, so we hope to get that within the next year. We did have a brief low DO trial, we called it. So we were operating with low DO with limited equipment, so not all the full equipment to go to SND. In the latter half of 2022, that's the yellow data there. And we were concerned with getting to those low DOs having high nitrous oxide emissions. We didn't see that. And that maybe is foreshadowing of not seeing that when we go to full SND operation. We'll see. Our South treatment plant is a lot larger than our Brightwater treatment plant. It treats about 70 MGD. It's a high rate conventional activated sludge treatment plant with an anaerobic selector PI control. It has 4 basins, each with a 4-pass serpentine plug flow design. The first pass is where our normally anaerobic zone is, at least the first half of the first pass, so about 1/8 of the total volume. And the second half of the first pass is aerated. That first pass is covered and goes to odor control. So we have partially covered basin, just that first pass. And when we operate seasonally now in Ledsec Edinger mode, where we're nitrifying, previously we weren't nitrifying, that anaerobic zone becomes anoxic. We did a baselining in 2021 where we were operating in our non-nitrifying conventional activated sludge configuration. During that time, we had aqueous probes in our the second pass of our aeration basin. We were limited in the cable length we had for those, so I would have preferred to locate them differently, but that's where we located them. We measured the nitrous oxide emissions at the odor control like we did at Brightwater. And then we had a floating flux chamber, which you can see there on the left, and tied that into our gaseous measurement analyzer for some of that baselining. Last summer, so 2024, when we were operating in a nitrifying condition, we placed the aqueous probes in a different location, one in the first pass, just downstream of the anoxic zone, and then one in the third pass. So the results of our baseline versus nitrifying comparison, I broke into 2 parts, gaseous analyzer measurements on the left at the odor control, and then aqueous analyzer measurements on the right. They have the same scale. That's why the left-hand graph is a little bit shrunk. What we saw when we measured the nitrous oxide emissions at the odor control was pretty much no difference between our non-nitrifying conventional activated sludge operation and our nitrifying LE mode, which was surprising to us, but that's what we saw. The aqueous measurements tell a little bit different story. You can see the 2021 data there in orange, and very little nitrous oxide emission estimated, and that's different from 2024, which was significantly higher. That is one potentially because of the probe location that are different, but also in 2021 we used the low range probes from Unisense, and the calibration was a little bit different. I'm not sure if we got that right, so I'm not 100% confident in that 2021 aqueous data. When I normalize that data to the influent TKN, what we see, again, the gaseous measurements at the odor control, really no change year to year. if we trust those aqueous measurements in 2021, we do see a pretty significant increase in the aqueous measurements. But I'd point out here that that aqueous sensor that we have, aqueous sensor 1, was located in the first pass, and our gaseous measurement was from the first pass. So those should have corresponding measurements. So there's a potential that the aqueous probes or aqueous analyzer is reading high. We don't have the luxury of having a fully covered basin like at Brightwater, so we have to extrapolate the data and take into more assumptions when we make these estimates. But in any event, any measurement here is much lower than the IPCC default value of 1.6% of the influent TKN going out as nitrous oxide. Some lessons learned. The aqueous probes are pretty easy to use. They don't require real frequent calibration. They have very good relative measurements, so you can track your emissions through time. The absolute measurement we saw at Brightwater needed an adjustment factor, but otherwise I think they'd be very good for control because of that. The relative tracking is very good. The one small drawback, the probe tip on the unit is glass, the membrane is glass. That can be delicate, I know from experience. And calibrating in really high or really cold temperatures is difficult because you have to calibrate it in a water bath that's your process temperature, and that can be somewhat difficult when it's really cold or hot. We're not a fan of the floating flux chamber. I didn't talk much about that from my baselining in 2021, but the data we got was over 3 days was pretty similar to the aqueous probe, but it ended up partially sinking. So it's not something we'll be using going forward. And then just we'll continue with the aqueous probes to characterize emissions when we go to SND at Brightwater. And we were somewhat surprised that our emission estimates are both lower than the IPCC default. That's all I had. Pass it over for questions.
Thank you so much, Aaron, for that lovely presentation. Also, thank you to Emma and Shannon for their presentation. So we're rapidly coming up to the end of our hour. We're going to try and squeeze in 1 or 2 quick questions, but we promise you that if we don't pick your question to answer, we will get you a written response in the coming days as a follow-up to the webinar. So our first quick question, Aaron, is for you, and it's building off of your recent comment about the gaseous phase measurements, the hoods, and there was a question about what were the specific challenges that you confronted? Was there anything beyond just them sinking that kept you from moving forward with that as an approach and using them for long-term monitoring? Some folks are reporting that they've had success in Europe and elsewhere using the gas phase measurement. So yeah, could you elaborate there?
Yeah, I think, the getting a good mass flow measurement of the gas that was coming off was somewhat difficult. And as Shannon and Emma pointed out, that's pretty critical. Just making sure there's like no low points in any of the tubing that could fill with moisture. And it was just sort of almost like two setups you have to worry about: the flux hood and then also the gaseous analyzer, and making sure the samples are all happy. So it's just more time and care going into that. I could see it working. I think we just gained pretty good confidence in the other 2 measurements, that the odor control and the aqueous probes, and didn't necessarily see a need to use the flux chamber anymore.
I will also add, just for the gas phase measurement in general, what I remember from my grad school days, that Teledyne analyzer used at the county is, designed for bench scale, lab scale, and Aaron had to do a lot of that retrofitting to equip it to be outdoors. I'd say in recent years, there have been some developments of, field-ready devices, whether portable or permanent. Kind of a more permanent one would treat it as kind of a flue gas analyzer, kind of. I think there are innovations that could help this for other utilities if they're looking into purchasing.
Awesome. So we're officially at the top of the hour, but we're going to try and squeeze one more question in if you're willing to bear with us. The next question is, a lot of the potential triggers for N2O look similar to process goals for some of the shortcut nitrogen removal processes being looked into now as ways to reduce carbon footprint utility. So I assume that that's about reducing energy consumption. Can you talk about the research into how N2O emissions might be related to some of those shortcut processes and sort of that balance between greenhouse gas emissions reductions from energy savings and increases in N2O emissions or potential increases in N2O emissions?
Yeah, I can start off on that, and then perhaps Aaron can talk about, the drivers with the SND at Brightwater. But yeah, I'd say it's a really good question, and it's an important area of active research at the moment. For example, low DO the idea is extremely popular. We're thinking about and actively putting into these full-scale treatment plants. And there is a huge amount of carbon savings if you're saving the electricity by operating at low DO. You saw on my slide that low DO is one of the parameters that's associated with elevated N2O emissions. But, while I say that, I actually do believe that it is possible to operate a low DO or suboxic, whatever you call it, DO system while having low N2O emissions. And, we've done some piloting work, initial work to investigate that, and we have observed it in certain instances, but it's an area of active research, and I think it's important for all these other research projects for low DO or saving carbon, whatever, these innovative processes, to be also monitoring N2O as they're doing their R&D with the vendors.
Okay, thank you for that, Shannon. I want to be respectful of everyone's time. Thank you for letting us squeeze in one more question. I'm going to pass the mic back to Harry to close us out for today.
Yeah, I just want to thank you for the great presentation by the speakers. I think, we encourage you, we answer the question, and also we encourage you to contact us. We have a network here. And also, you'll be aware, I think we have Research Foundation have over $1 million ongoing research. So keep up with our newsletter, or maybe even in next year. And then on the December 12th, we have another session in this series. So thank you very much. For your joining.